Hello everyone. So in this session, we will start with a new topic, which is numerical integration. So first, let us ask ourselves, what is the integral of a function? The integral of a function is nothing but the area of the graph of the function under um, or the area under the graph of the function between the 2 points that you are integrating between. Let's see, this is a and b, and if this is our function, then the integral is the area under this curve. So it's everything that lies between these 2 points. All of this area we want to compute is the integral of this. So this is what we should try to understand in this topic. This is the integral. You'll have possibly done a little of this in high secondary. So numerical integration gives us some techniques to try to estimate this value. And I mean estimate, not give us the exact value of the integral. Okay, so the basic idea of numerical integration which we will use is like this. So many times the integral is difficult to compute. So what we are going to do is, if you are given a function, let us try to draw it again here. Say this is a function is something like this. Okay, and we want to integrate between the points a and b. So the basic idea of integrating, so many times as we said, functions are difficult to integrate. What we will do is we take points close together on the graph, okay, where the x coordinates are equally spaced. In our methods, we are going to only look where the x coordinates are equal. So we'll take these points close to each other. This from A to B, and we will, using polynomial interpolation, which we'll have studied, we will find some polynomials passing through these points. Okay, say we might find a polynomial passing through the points, the first 4 points first, passing through the first 4 points, we might find a polynomial passing through it. Then find another polynomial passing through the next 4 points. In case we can look at 4, but there is no restriction on what we could possibly use. And find another polynomial passing through next 4 points. Now, as we know, polynomials are very easy to integrate. So we could compute the integral under these polynomials. Put the integral under each of these polynomials. And since these polynomials, since you have taken these points very close to each other, you would expect that these polynomials almost estimate the values of the function, and which would mean that the integrals, the sum of these 4 integrals would actually estimate the integral of the function. This would be the basic principle. Okay, so this could be something like y1. This first polynomial could be y1, second polynomial could be y2, third polynomial could be y3, and the integral of f would now be approximately the integral from, call this as x naught, one is x1, x2, eight, 9. So this would be nothing but this would be approximately x0 to x3 y1 plus the integral from x3 to x6 y2 plus the integral from 6 to x9 y3. Okay, this would be the technique that we use to estimate integral. So for the first method, which is the trapezoidal rule, what we will be doing is we will be looking at linear polynomials passing through 2 points, not polynomials of degree 2 or 3. This would be polynomials of degree 3, but we will be looking at linear polynomials. This is the easiest method. So suppose we are given a function that we want to integrate with the integral a comma b, and x naught equals a, x1 up to xn are points in R which are equally spaced, say in this manner, that is xi is equal to a plus ih, and for any I equals 0 to n, we let yi be f of xi, f of these points here, x0, x1 up to xn. Then what would be the linear polynomial or the line that passes through the point xi minus 1 comma yi minus 1 and f of xi comma yi. Okay, so let us see what we are geometrically looking at first. So in this case, we have the function f, we have these points x0, x1, 2, 3, 4, and so on, okay, up to say some xn, and corresponding to that here, these would be your point x0 comma y0, okay, on the function x1 comma y1, 2 comma y2 would be x3 comma y3, and so on up to, okay, let us take the point -1 here. This would be xn minus 1 or yn minus 1. This would be xn comma yn. So this is what we have. So what we'll be doing for the trapezoidal rule is we will be looking at the linear polynomial or the line passing through the consecutive 2 points. The first one, right? The first one, which we are calling as we can see here, this is y1. I think we are y11. So this is the polynomial y1. Okay. Then this would be the polynomial, the line y12 that passes through the x1 y1 and x2 y2. This would be y12. This is y1 2. Then we look at polynomial passing through the next 2 points. Okay. Of course, these are extended, but I'm only interested in their values between the 2 points. So I will only draw this much. This is my y13. Okay. 1 signifies that it is a polynomial of degree 1, and we can keep doing that up to, let's say, here would be our y1n. Okay, now just like in the what we have seen earlier, what we will be doing is we'll be finding the the integrals over these particular we'll be finding the integrals over these particular functions, okay, and adding them all up. That's what we will be doing. So the trapezoidal rule, we have to integrate over this line from x0 to x1, and then from x1 to x2, then from x2 to x3, and so on, and add up all the integrals. That's what we're looking to do. Okay, so let's see here. So what is the line segment that passes through the point xi minus 1, yi minus 1, and xi, yi? So between any two consecutive points, okay, I goes from 1 to n. So essentially what we're looking at is first x0 y0 to x1 y1, and then x1 y1 to x2 y2, and so on. To simplify it, we can just do it all in one go by doing xi minus 1, yi minus 1 to xi, yi. Okay, so this would be the line segment. You all know how to get this equation. Now we know that xi is nothing but a plus ih. Yeah, there are some errors here. This is not x1, this is xi minus xi minus 1, and this is also xi minus 1, this is yi minus 1. Okay, so please take note of the correction. So here this would be equal to yi minus 1. And what is this xi minus 1? Okay, so we are given that xi is a plus ih, xi is a plus ih. So for every I, so xi minus 1 would be a plus I minus 1 times h. So if we subtract this, we get, okay, we'll get h. You can check and see. You will get h. Okay, essentially h is the distance between any two consecutive points here, the x-axis. So this is what the equation of the line is. So we now need to integrate this. So what happens when we integrate this? We want to integrate y1i from xi minus 1 to xi, right? You can see here we want to integrate y11 from x0 to x1, y12 from x1 to x2, 13 from x2 to x3. In general, we want to integrate y1i from xi minus 1 to xi. So what do we get when we integrate this? These are all constants with respect to x. So we can pull that out of the integral, and we are integrating from xi minus 1 to xi. What we are integrating? X minus xi minus 1 dx plus this. So to compute this integral, let us make this substitution, that is, we'll put x equals t plus xi minus 1, that and when we make the substitution, dx would become dt. So this integral, we know the method of substitution. This would give us yi minus 1 by h, and then the integral would go from, because when x is xi minus 1, when x is equal to xi minus 1, t would be 0, and when x is xi, t would be, so if x is xi minus 1, okay, t would be 0, and when x is xi, then t would be nothing but xi minus 1, which would be h. Okay, so this is h, t dt plus this is what we have. This is dt, okay, and you integrate this, you'll get y minus 1 by h square by 2 plus yi minus 1 h. Cancel out the h's. This is what you get. Now add, you'll get h by 2 y minus 1 plus y. So this turns out to be a very nice simple integral. So let's see what happens when we add up all these integrals. So as we said, the integral of f is approximately, so the integral of f we know is going to be the integral from x0 to x1, x1 to x2 plus up to xn minus 1 to xn. Okay, this is what we know by the rules of integration. So each of these would be approximately, because we have taken those points close to each other, or that's what we are assuming. These would be equal to, almost equal to, x0 to x1, estimate by the y11, y12 to y1n. Okay, now you can see this integral is nothing but h by 2 yi minus 1 plus yi. So what we have here is h by 2. Okay, the first one will have y0 plus y1. So this is 1. For I it is I minus 1 plus I, and here you will have y1 plus y2 up to yn minus 1 plus yn. Okay, so now when you add all of this, what happens? The two last, the numbers on the left end and the right end are added only once. Okay, these two are added just once, that is, this one and this one are added just once. So we put them here, so that is y0 plus yn plus every other point. You can see y1 would be added twice, y2 would be added twice, yn minus 1 would be added twice. Okay, so plus twice y1 plus y2 up to yn minus 1. This is what the formula is. Okay, so this is the formula for your trapezoidal rule. Okay, so let's look at one problem. Let us solve one problem using the trapezoidal rule. So using the trapezoidal rule, let us estimate this integral, that is x raised to 7 plus 9x square plus 1, by taking 5 equally spaced points in the interval. Now, if we want 5 equally spaced points in the interval, you can check and see, when we want some m equally spaced points in an interval, so that is a going from x0, x1, x2 up to b equals xm. Okay, if we want m equally spaced points, okay, then this breaks the interval into m minus 1 sub intervals. Okay, so when you take 3 equally spaced points, sorry, when you take 4 equally spaced points, that is here you can see x0, x1, 2, x3, it breaks the interval into 4 equally spaced points. So the value of h would be the length of the interval, that is x3 minus x0 divided by 3. Okay. When you take 4 equally spaced points, it breaks the interval into 3 sub-intervals. When you take m equally spaced points, okay, when we take m equally spaced points, by the way, this will be m minus 1. When we take m equally spaced points, it will break the interval into m minus 1 subintervals. Okay. So the value of h would be p minus a by m minus 1, and b is 2, a is 1, m is 5, so you will get 0.25. So what will be the value of x0? x0 will be 1, x1 would be x0 plus h, x2 would be x1 plus another h, x3 would be x2 plus another h, and x4 would be x3 plus another h. Okay, so x0 plus h would be 1.25, x1 plus h would be 1.25 plus 0.25, which is 1.5, x2 would be 1.5 plus 0.25, which is 1.75, and add another 0.25 to it, you get 2. Okay, now you need to compute the values of y0 by simply plugging in what this is over here. So the first one would be when x0 is 1, since x0 is 1, the value of f would be 1 raised to 7 plus 9 times 1 square plus 1, which is nothing but 11. This is 1 plus 9 plus 1. X1 is 1.25, so you put this in here. You can use your calculator and you can see this is nothing but 19.831. Of course, rounded up to the third decimal place. Okay, we'll be rounding off at third decimal. Third decimal. And similarly, we can compute what is y2, y3, and y4. Now, by the trapezoidal rule, this integral would be approximately h by 2, that is 0.25 divided by 2 into, okay, y0, that is 11, plus y4, that's the last one, that is 165, plus twice everything else, that is what is left out here is yeah, there is a mistake here. So this would also, you would need to add 19.831, and the value that you get here would be 56.24875, okay, or 249. Okay, this is 56.249. Okay, this is what you will get here, and if you look at the actual value, it is just 53.875. So you can see that the values of the integral are quite close. Of course, if you want to estimate it better, instead of taking 5 points, you can take 15 points. Okay, that will give you a better approximation. You can try that. You can increase the number of points. Okay, or you can write a Python program for it, and then you can run it for as many points as you like. So we can stop with this, and I will see you next time. Thank you.